Okay, thanks, Martin. Once again, thanks to invited me. I hope to show you here the state of art of my PhD work that have been done under the supervision of Alexis Rigo at INS in Paris and in collaboration with Efthimios Sokos from Patras University in Greece. Today, I will talk about micro-seismicity, seismic wave velocity model, and earthquake clustering in Western Greece, and more precisely in the Akarnanian region. So here are the outlines of the presentation. We will start with a quick view on the general and more local geological context and continue with presentation of the micro-seismic survey, thanks to Madame Seismic campaign. Therefore, I will present a new seismic velocity model for the region and pass on the results with structures highlighted by the micro-seismicity. First, cluster location and their physical processes, the background seismicity, and a seismic plant located towards the Korean Gulf. And to finish, the outlooks, because my work is still in process, then we still have many questions and analysis to do. So about the general context, we are in Greece, here on the red square, between different large-scale structures. The North Anatolian Fault with strike-slip right lateral motion, which is responsible at his west end of extensional diffusive movement. The subduction zone here between Nubian plates and Anatolian plates, which is associated with the Hellenic arc just here. This subduction zone rotates on Western Greece in a more complex structure in strike slip. Here's the Kefalonia Fault, just here, that mark the southeast limit of the Eurasian plate on this region. Then we are in the middle of those biggest structures, and there is a microplate highlighted by Eugénie Perrouse in 2013, named the Island Akarnanian Block, IAB. This microplate is located to the northwest of Korean Gulf. Here, that's an extensional zone, and to the east of the Kefalonia Fault, just here, that mark the limit with the Eurasian plate. This IAB block are also bordered to the north by normal faults, the Loutraki faults, here on the Ambrakico Gulf, and to the east by strike-slip fault system, the Katuna-Stamna fault system here. We can also see other systems like normal faults in the Patras Gulf and around the Tricony Snake, that is a graben system with normal fault on each side. The geophysical link between all those local scale system and biggest scale structure are still difficult to appraise. That's why I start this work. To have a better understanding of what happened in terms of seismotectonics in this area, we will construct a local seismotectonics model consistent with tectonic observation and geodynamic setting already known. To do that, we use precise micro-seismic data thanks to a new dense seismic campaign. And this is the seismic campaign that are the network, the complete network used in this study. You can see permanent network in dark purple here, but are not so deployed in the area and more around the Korean Gulf. To have better data in the area, we start a seismic campaign named MADAM in October 2015 and put 16 seismic stations in lighter purple in all the area. Those seismic stations are recording continuously. Here you can see a graphic with the variability station. You can see that more of the network have been installed at the beginning of 2016. Some of them have recording stops due to problems with batteries, power, memory, and other many problems. To the right, it's just a picture with Alexis, my supervisor, at SS06 station, trying to find a better place for the station. This campaign recorded for more than 3 years, actually. To detect micro-seismic events that in data, we use a non-made program with Python and more precisely with OBSPy to detect seismic events on the continuous recording. This program works with short-term average, long-term average detecting method after applying a filter between 2 and 10 Hertz. There is an automatic pick with visual check and the possibility of manual correction. Thanks to this data picking method, we have detected a huge quantity of events, more than 13,500 between 2016 and 2018, then 3 years of data. This huge quantity of data allows us to constrain precisely a velocity model for all the area. From a local velocity model that already exists, but only constrained for the north part of our area, we do first location and we select events that are more precisely located with good quality. It's mean less error and RMS below 0.35. We also determine the VP over VS ratio that are at 1.85. And we take a look on the control place on map to see where our velocity model are better constrained. You can see here a map with all the trajectories between events and station, where the events are detected. We cover Trichonis Lake region, the Stamna faults, but also the Katuna faults and around Amphilochia and Navpactos city. In total, it's 2,300 seismic events that have been used to constrain our velocity model. And this is the model in green on the graphic. This model are between surface and 14 kilometers depth and cover all the region from Andrakico Gulf to the north to Patras Gulf to the south. If we compare with others models from the same region, we can discuss about differences. The Aslinger et al. Model in 98 in red, here that have a slow seismic layer at the surface is really close to our model, despite that this model, the Aslinger model, use data only from the north part of the zone and not take in account the area around Patras and Corinne Gulf. Also, if we take a look on the Casaras et al. Model 2016 in purple around the Trichonis Lake, we can see big differences with our model, while we also constrain the Trichonis Lake area. that may suggest a non-negligible lateral variation in terms of wave velocity. With our new seismic model, we locate all events that are enough good quality to be located. 11,000 events are located in the orange dot on map. Before, the only catalog existed on this zone was the National Observatory of Athens catalog, NORA, and here it's almost 4 times more events that are located. With the new seismic model, velocity model, compared to the model used by NOA, for all Greece, the events are less deeper. We are at a maximum around 13 compared to 14 kilometers depth for the NOA. To the right, you have the map with seismic event location and cross-section north-south and east-west. You can see some specific structure that stand out from the map and cross-section. First, events that are really close to each other, for example, here or here, and we can see also in map here or here or here. And this is then close to each other in location, but also, and you have to trust me about that, in time. And this is clusters physical phenomenon. You can maybe also note in map and in north-south cross-section a strange planned seismic structure around Appraise city that seems to deep northward. Then now we pass to see those different structures more in detail. First, clusters. I know that there is no fixed definition of what is a cluster. Then here, clusters are geographical, but also temporal constraint. The characteristics are minimum of 6 events, 10 days of maximum look between 2 events, 10-kilometer ray interaction, and a confidence level on those criteria up to 0.99. In total, 53 clusters have been highlighted on all the area: Mesology Zone, Patras Gulf, north of Corinne Gulf, Trichonis Lake, Katuna Faults, and around Amphinokia, and on the north part of Gulf of Ambracico. To once again locate more precisely, but this time relatively clusters, we use a double difference method, hypotd, that allow us to have an idea on the cluster geometry. The next slide is an example of a seismic cluster just here at north of Trichonis Gulf in yellow. And you have to the left the location with the velocity model on HIPPO 71, and to the right the relocation with double difference method. Here is the map. The structures are completely better highlighted on the location map, as we can see here. Here you can also see structure in 3D with what looks like a fault plan here. And here are the error bars that are clearly better with double difference methods. That was for cluster geometry, but we also take a look on timeline, and we detect for some of them, for some of clusters, particular velocity region. An example of one cluster located around current Patras Gulf region on red circle on maps. It's here. The plots are the in-plane distance in meters as a function of time in days. To the left, you have the data, and to the right, the interpretation. The starting point is the first event detected in time, and the distance is calculated relatively to this first point. Inside a cluster, we can see circle with many activity and less activity. In general, those cycle activity propagate at speed of tens of kilometers per day, correspond to 0.10 meters per second, speed of slow seismic events, the slope in blue here. This specific region is also detected on cluster around Sokos Lake, red circle here. This is another example around this Sokos Lake. We can draw a maximum distance of events is the top of the graphic. And this top seems to increase as a function of time. That suggests a velocity of the rupture front. This rupture front propagation are calculated around tens of meters per day, feed migration speed in the orange line. Here's the orange line just here. Those specific regimes have already been observed by Gao et al. In 2012, where they was talking about feed migration, which causes a release of pressure on faults and induce slow seismic events with micro-seismic event cascading that propagate at slow steep speeds, 10 of kilometers per day, with a general regime at feed propagations, 10 of meters per day. We could discuss about why we don't see this regime in all our cluster. Is there because we don't have enough data to see it, or because we don't have fluid sources? And so it's not the same region that are in all our cluster. We have to investigate furthermore to answer to these questions. But pass to another type of events visible in our data, the background seismicity. Even if we have many clusters, we also have background seismicity well distributed on all the area and well distributed in time also. We still have to process on this work, but we can already see a huge quantity of seismic events at east of Amphilochia that ask questions. And if we zoom in, here we can we can also see events between Katuna and Stamna faults, and also along the Katuna faults here. Pass now about the seismic plan that we have detected on the network. Here we extract data for this plan like a giant cluster, but without the time constraint. First, this map shows the location of the seismic plan in between Patras and Corinth Gulf. And here is the 3D map to have an idea about his shape. It's not so easy to see in 2D. This plan are 13 kilometers wide, between 5 and 15 kilometers depth, so quite deep actually, and almost continuously active. This graphic showed the in-plane distance as a function of time. At some moment, there is a seismic gap for tens to hundreds days, but we didn't see any seasonal or other link or reason about for that. This seismic plan have been already seen by Clara Duverger in 2017 during her PhD. If we focus on its geometry, it's dipping towards north. On north-south cross-section, we can clearly see the dip from 5 to 15 kilometers depth, with maybe a small flat form at the south part. The east-west cross-section highlighted a bowl-shaped form here or here with an axis, what looks like an axis in the middle of the plan here. Now we look on other direction because there is something, as we can see, something more eastward at east and more westward at west. If we look at 145 degrees, we see the west part here tipping to the west and the east part almost flat. Same thing on this cross section or in this one. Same thing for the 45-degree bit, but reverse. That show then a dip on of east part at east and nothing at west. It's really clearly visible on this cross section here. There is a changing of on type direction from east to west, but once again we have to go farther to better understand this shape and the structure and the link between all of that. That was my work since now, and I still have many work to do. But to have an idea of what is need to be done, here is the outlooks. First, which faults are associated with clusters and background seismicity? For that, we have to determine focal mechanisms and associate it with cluster geometry and with faults location and movement. About our cluster on Trichonis Lake region and Corinne Gulf region, can we really talk about slow slip events induced by fluid migration? To know if there is a propagation, we can see the repeaters on network that we have already seen on data processing, but not extracts. And we know that there is repeaters. We can find and look at them. It will allow us to fix asperities on faults. To link the size and velocity rupture, we can calculate effective magnitude for all the cluster because that had two parameters linked. And to find the fluid migration origin, we can have a look on the start cluster location to determine where the fluid comes from. And the last point, to understand what is this seismic plant, is there a detachment plan from inherited structure, but up to 15 kilometers depth? Is it not so too deep? We can see links between Corinne Gulf, just to the east, and maybe relocate this plan with another velocity model closer to Corinne Gulf velocity model, because we know that there are possibility of lateral variation in our model. Okay, then to conclude, we develop a new and robust local velocity model, which allow us to better constrain the location of micro-seismic events in all the area. Cluster structure are highlighted in the wall area here. Specific physical processes around Corinne Gulf and Triconus Lake are shown in the cluster with slow and fast velocity propagation. The background seismicity have been located with seismicity between fault, and on area. And a large seismic plan creeping continuously have been located at the westward limits of Corinne Gulf, with east-west deep variation from northeast to northwest. Thanks for your attention.